Good day, students. You are welcome to another wonderful episode of your darling program, Schoolonair Physics. On the previous episode, we were looking at some things about the spherical mirrors. We talked about plane mirrors and the images formed by them, their characteristics. And then we set our hands on the spherical mirrors. We talked about the concave and the convex, and then some properties, like the principal focus, the principal axis, the center of curvature, the radius of curvature, the pole, and the rest of them. But in that episode, we were cut short by time. And we are here again today, so we shall be continuing on that particular topic. So today, we should start by looking at the characteristics of ray diagrams of spherical mirrors. Characteristics of ray diagrams of spherical mirrors. That is, when objects are placed at various positions on a curved mirror, what should we expect? What should we expect? Okay, so first today we're going to look at a ray parallel to the principal axis. When a ray is parallel to the principal axis, it is expected that it is reflected through the principal focus. So when a ray is parallel to the principal axis of a curved mirror, it will be reflected through the principal focus. Remember, I told us that the principal focus of a whether concave or convex mirror is the point on the mirror where all rays parallel to and close to the principal axis appear to diverge or converge after reflection. So when a ray is parallel to the principal axis, it will be reflected through the principal focus of that particular mirror. And when you have a ray that is passing through the center of curvature, which hits the mirror normally, it's incident on the mirror normally, and it passes through the center of curvature C, it is reflected back along its own path. So it does not reflect up or down. It goes back through the center of the mirror. So when a ray is passing through the center of curvature, the reflection is also, it's retracing a step back through the center of curvature. So it's reflected back along its own path. And then when we have a ray that is through the center of curvature, which is the mirror normally, we said it's reflected back along its own path. So I've said that. And then when you have a ray through the principal focus, when you have a ray that is passing through the principal focus, F, it is reflected back parallel to the principal axis. So it's like the principal axis and the focus, they are always working together. Because when you have a ray through the principal axis, it is reflected through the principal focus. And now that you're having a ray through the principal focus, it's reflected back parallel to the principal axis. Now, when we have an object that is behind the center of curvature, we have an object beyond C. The image is formed between the center of curvature and the principal focus. Between the center of curvature and then the principal focus. So we have the image between C and F. And of course, the characteristics of the image is always real and then inverted. Now, those are the two things you need to take note of here. The image is inverted and diminished. That is, if it's upright, if the object is upright, the image you are getting in the mirror will be upside down. It's inverted. And apart from that, the image becomes smaller. It is diminished. So when you have object placed beyond C, that is beyond the center of curvature, the image you will have will be inverted and will be diminished. But of course, the image is always real, and you will see the image being formed between C and F. Now, when an object is placed between C and F, when you have object between C and F, the image is beyond C. Now, the other time I told you that the principal axis and the principal focus, they are working together. Now you have the object behind C and then the position between C and F working together. So when you have an object between C and F, the image is beyond C. Of course, again, the image is always real, inverted, but in this case, magnified. So instead of having it diminished, the image is enlarged. The image is magnified. And then when we have object placed centrally at C, that is the center of curvature, when you have an object placed at the center of curvature, the image is also formed at that center of curvature. The only thing we have there is that the image will be inverted. The image will be inverted, same size as the object, real. Okay, so just take note of all these properties. And then when we have objects placed between F and P, when an object is between F and P, the image is behind the mirror. And of course, when an image is formed behind the mirror, it is always virtual. It is never real. That's why such images are represented with broken lines. So they are virtual, erect, and magnified. And of course, when we have our object placed at F, the image is formed at infinity. Most of the time, it's not seen on the screen. It's just assumed that the image is lost somewhere. So when object is positioned at F, at the principal focus, then the image will not be seen on the screen. It will be far, far, far away beyond the perimeter of the screen. Now, the convex mirror, that's for concave. The convex mirror. In a convex mirror, the image is always formed behind the mirror, irrespective of the position of the object. You know, for the concave mirror, we're talking of if the object is placed at C, if it's at F, it's between C and F. We talked about where the images are formed. With convex, irrespective of where the object is placed, the position of the image is always behind the mirror. It's always behind the mirror. And of course, the image is always virtual, always erect, all of them, always erect and then diminished. So the image is always smaller in size, although it is erect and virtual. Okay, so that's for convex. So we can have a comparison of real image and virtual images. Real image and virtual image. Now, the real image is formed by intersection of real light rays. Real light rays. And then virtual image is formed by apparent intersection. You know, when we were defining principal focus, we said where rays parallel to the principal appear to diverge. Make sure anytime you are defining principal focus, that word appear, seems, is important. Because these things are not actually things. We believe that probably that is where they come from. So where they appear to diverge. So that's why the word apparent is used here. So real image is formed by intersection of real light rays, while virtual images are formed by apparent intersection of light rays. And then also, real image can be observed on the screen. Virtual images cannot be observed on the screen. That's why we use broken lines when we are drawing ray diagrams. We use broken lines to represent virtual images. Number 3 is that the real image actually exists, but virtual images, they appear to exist. You know, I emphasize the word appear. We don't really see them, but we believe probably they are there. So we say they appear. That's why we say they are virtual. Then it is always, the real image is always in front of the mirror. Virtual images are always formed behind the mirror, as we have with convex mirrors. They are always behind. That is why convex mirrors are always producing virtual images. They are behind the mirror. And then real images the real image is always inverted, but virtual image is always erect. That's one positive thing about virtual images. It's always erect, but real image is always inverted. Okay, so having said that, let's quickly take a look at something also more important with mirror, and that is the mirror formula. The mirror formula. So if you consider an object placed at a distance u of a curved mirror, and the image formed at a distance v from the mirror, and the focal length of the mirror is f. Again, I say the object is placed at a distance u from the mirror, and then the image is formed at a distance v from the mirror, and the focal length of the mirror is f. The equation connecting the three of them, the relationship between the image distance, the object distance from the mirror, and the focal length of the mirror is represented by, you have 1 over u plus 1 over v is equal to 1 over f. Keeping in mind that your u is the object distance from the mirror, your v is the image distance from the mirror, and f is the focal length of the mirror. So you have your 1 over u plus 1 over v being equal to 1 over f as the mirror formula. Now, all distances, you have to keep in mind this. Having known that 1 over u plus 1 over v is equal to 1 over f, there are instances where your plus changes to minus. And what are the conditions responsible for this? Now, all distances of real objects and real images are positive. So when I have real objects and I have real image, then my 1 over u and my 1 over v will always be positive. Okay? And why distances of virtual objects and images are negative? So if I have a virtual, like we have in convex, so instead of us having 1 over u plus 1 over v equal 1 over f, I will end up with 1 over u minus 1 over v, because the image, which is supposed to be v, the image distance, is a virtual. The image is a virtual image, so I'm going to have minus, a negative. So also, the linear magnification produced by the mirror is given by the relation. When you have the magnification, is given by the relation m is equal to length of the image over length of the object. So we have a v over u. That is when we are trying to see the size. What's the size of the image that is produced? Is it bigger than the object, or is it smaller? By how much is it bigger, and by how much is it smaller? So that's what we mean by the magnification. So the length of the image over the length of the object. So let's take a look at an example. The example one we have here is saying that an object is placed 50 centimeters in front of a concave mirror. Keep in mind, this one is a concave mirror, so we are working with all positives. Okay, so an object is placed 50 centimeters in front of a concave mirror, and the real image is produced 20 centimeters from the mirror. So this is our object distance from the mirror, 50 centimeters, and then this is the image distance from the mirror, 20 centimeters. Now, the question number one is, what is the magnification produced? B part is saying, what magnification will produce if the object is placed 20 centimeters? If the object is not placed 50 centimeters, if it is placed 20 centimeters, what will be the magnification that would be produced? So, solution, you recall that we said magnification is equal to what? Image height over object height, which is the same thing as what? Image distance over object distance. So in this case, the object distance that is given to us is 50 centimeters, and the image distance from the mirror that is given to us is 20 centimeters. So in this case, our magnification again is what? Object distance over image distance. So we have 50 over 20, and that gives us what? 2.5. So this means that the image is enlarged. So by the time you have your magnification greater than 1, that means that the image is enlarged. And when your magnification is less than 1, that means that what? The image is diminished. So in this case, our magnification is 2.5, far greater than 1. So we say that the image is enlarged. Now, the other part of that question says that what will the magnification be if the object is placed 20 centimeters from the mirror? So in that means, in this case, the object distance is what? 20 centimeters, and the image distance still remains 20 centimeters. So our magnification will be what? Object distance over image distance, which is what? 20 over 20, and that gives us what? 1. So when that happens, we say that this means that what? The image will be the same size as the object. So let's take note of that. When you have a magnification of 1, what it interprets into is that the image size is the same, or distance is the same as that of the object. And when you have a magnification greater than 1, that means the image is enlarged. When you have a magnification less than 1, that means that the image is diminished. Okay, so quickly let's take a look at another example. Example 2. An object is located 30 centimeters from a converging mirror with radius of curvature of 10 centimeters. Now, we are given radius of curvature. Remember the relationship between radius of curvature and focal length. Your radius of curvature is 2 times focal length, which means that your focal length will be radius of curvature divided by 2. So keep that in mind. Now, A, at what distance from the mirror will the image be formed? And B, if the object is 4 centimeters tall, how tall is its image? Now, the first thing we do is that we were given radius of curvature to be 10.0 centimeters. So I told us that our focal length is half of radius of curvature. So you have half over 2, that gives us what? 5 centimeters. So going back to our mirror formula, 1 over u plus 1 over v equal 1 over f. So we have 1 over 30. We don't have the image size there. Okay, our image distance. So we have 1 over 30 plus 1 over v equal 1 over 5. Such that our 1 over v would be what? 1 over 5 minus 1 over 30. So you do the arithmetic there. Your 1 over v equal 5 over 30. And then, of course, your v is equal to 6 centimeters. So the image will be formed at a distance of 6 centimeters from the mirror. And then the other part, we have the relationship h naught, that is the object height over image height, is equal to the object distance over image distance, such that if you make your image distance the subject of the formula, image height, so that you have your v over u times the object height, such that we have 6 over 3 times 4. That gives us 0.8 centimeter. So that's the much we will take today on on mirror, the curved mirrors, and then of course the properties, how their images are formed, and of course some basic calculations that has to do with the mirror formula. But then I will not just leave you. I will have you lay your hand on some problems, and let's quickly take a look at this. First one is asking you to distinguish between a real and a virtual image. We've talked at length about that today, so try and do it on your own. Distinguish between a real and a virtual image. And then 2, a pole 6 meters long. Take a look at this. A pole 6 meters long is laid along the axis of a convex mirror of radius of curvature. Now, be careful here. You are given radius of curvature, okay? So you know what you have to do in obtaining your focal length. Radius of curvature 3 meters. The end of the pole nearer the mirror is 2 meters from the mirror. So you have to calculate the length of the pole seen in the mirror. Be very, very careful when you lay your hand on that. And of course, when you are through with that, as usual, you can also send your answer to the address that rolls beneath your screen. I will definitely receive them and do justice to them. If you have any other problem, as usual, you have that address. You can always forward it to it, and I will be glad to treat your problems. So that is the point at which I will be leaving you today. Hopefully, we will be together soon on another episode. But between that time and now, enjoy yourself and have a wonderful time. Bye for now.